This is the basic view of this. This was originally for a moon-based competition. However, with slight modifications, it also works on Mars. We're going to talk about it in both roles. So there we go. This is my usual table of the grand challenges of space settlement. If you've been to any of my talks for the last few years, you've seen this before. It starts at the top left with each column representing the challenges at a given distance from Earth. SpaceX Starship breaks the top corner, which enables the path forward. By using Starship as a foundation, we open all the challenges shown in orange. This allows us to solve most of the problems of becoming a multiplanetary species. So in 2019, I presented a 1,000-person settlement on Mars called Eureka. Since it was a surface study, it did not cover issues like orbital refueling or debris. So the following year, I presented StarPort. This was designed as a logistic solution, but it also lets you put a large space city of up to 1,000 people anywhere in the solar system. However, there's still a major gap between first landings and permanent outposts. So this year, we closed that gap with the InSight surface base. The principle is simple. You must transition from ships to ports to make any permanent gains. Otherwise, you're just visiting. So the transition from exploration to commerce is complex because many of the engineering goals are the exact opposites. Exploration means traveling light for short periods. Exploration systems like Apollo do not translate well to heavy permanent structures for long-term habitation. They also have custom systems for each piece that are not necessarily easily replaced 5 or 10, 15 years down the road. So even with Starship, the conversion is complex because the two different design languages are entirely different. We need to think a bit more like plumbers and electricians maintaining a 100-year-old house than rocket scientists. So on to InSight. There are 3 main building types. This is the outpost habitat. To build this, we start with 4 lunar starships or Martian starships next to each other on a foundation. Then we build the walls to block radiation and thermal stress around them. The walls are built with frames brought from Earth initially. These frames can then be filled essentially with interlocking sandbags. These bags are filled with moon dust and cindered with microwaves and settled in place. We'll talk about the Martian version of this later. And settlers would then use the extended tower workspace like an unfinished basement or garage. They would determine how much atmospheric pressure it can hold and then extend to living and working and agricultural spaces into that volume just outside the door. In these early stages, the fuel tanks in the starships would be converted to LED greenhouses to sustain the outpost. One starship could feed and house 10 settlers in this way, with the fuel tanks being the greenhouses and the upper parts being the living quarters. This drastically reduces the food imports from Earth. It also allows each tower in this configuration with 4 starships to hold 40 people. The exterior of the structure has emergency solar panels, fiber optic light for light gathering systems for the greenhouses, and periscope windows. Using the periscopes like this gives the settlers at any level of the habitat a top floor view. And note the lunar starship over here to scale. This is your periscope window along the top edge here. And the flying buttress construction, frankly, is to make it look a little less brutalist. I wanted to make something elegant, not ugly. The hexagon structure has a 22-meter baseline to keep the foundations future-proof. I wanted these hexagonal structures for space settlement to allow for future starship designs up to 18 meters in diameter or larger. Elon Musk mentioned this in a tweet one time that this was the maximum size that a starship could be. Settlement designs must have an architecture that can be maintained in living economies over centuries, just like our homes do today. You want standard sizes for construction, pipes, brickwork, and so on to be able to do ongoing maintenance. Now on to the spaceport. The goal of the spaceport is to get the exhaust plumes from arriving spacecraft as far away from the surface rock as possible, particularly in the case of the moon, because you can actually eject dust and rocks into orbit and have it hit you weeks later. In this configuration, a visiting starship's exhaust plume is never closer than 100 meters from the surrounding surface. The angled panels have an open-face pattern of Tesla valves that redirect the plume back on itself. This would help protect the panels from blast damage. And yes, the elevator was expired by the ones from 2001 and Space 1999. You would basically lower the vehicle directly into the center and then push it off to the side to do maintenance. An area within the vicinity of the landing site would also be scrubbed of dust during the construction process, because you needed that to build the sandbags of the structure. If you added a tower similar to the ones being built in Boca Chica, then you could use the catch arms and also have easier crew access. As with Habitat, you could put up to 7 starships on the inside, and some of those could be converted to fuel storage with the oxygen made locally on the moon, or both propellants on Mars. So a little bit about power supply and demand. The greenhouses that I mentioned, if they are LED based, especially during the lunar night, or during the global dust storms on Mars, you have the same problem where you just need to be able to maintain lighting. Those would actually consume the vast majority of the power for the base compared to the human operations. So the basic idea here is that we have a power plant that is meant to be cheap, long-lasting, and low maintenance. So we use low-enriched uranium, similar to the systems that were described yesterday in the nuclear power thing. Those systems can last actually 200 years without refueling. They're actually, it's not nearly as much power, but it's much more consistent and much easier to maintain and much safer. So you make the plants bigger, but at these scales, they don't really, they can still be very powerful, but not very large. So these are basically shipping container sized systems with large radiators. On the moon, you would actually use solar panels to shade the radiators to increase the efficiency during the daytime. And then at night, of course, the radiators would work at full capacity because they would be just radiating directly into space. They wouldn't have to worry about sunlight offsetting their ability to radiate energy. So here's the Mars version, and yes, I did just tint the background, but we're going to get into a few more differences here. This goes back to the original Eureka design. Basically, the outer layer of the system is water ice that is reinforced like with either a fiberglass or other sort of matrix. This goes back to the idea of PYKRETE, which was invented in World War II and was basically sawdust reinforced ice that was almost as hard as concrete. They later found that if you use newspaper, you could actually make it as strong or stronger than concrete. So in this case, we would be going all out and going with something that would be more like fiberglass or Spectraline or something like that inside the bricks. It would basically almost be like steel wool in there. But it would be laid out specifically along those patterns. And those would simply be deflated and inflated on the surface and then filled with water and frozen into place. The seals between the gaps here are, this is exaggerated in scale, but the nice thing about these is that if the brick expands or contracts, if it expands, it stretches in one direction, and if it contracts, it stretches in the other direction, but the seal is maintained. You'll see these in log cabins for the boards between the things. You'll see them in decks for docks and so forth. So there's a very common technique for maintaining a seal. The outer layer would be water ice. The inner layer, you could probably use something more like the surface clays to make something more akin to a ceramic brick for the inside, because the room temperature on the inside is not going to be conducive to maintaining that ice layer on the inside. But this allows for good cosmic ray shielding because water ice is a better material for that. In addition to that, we can add what's called a Hallbeck array, which is basically you turn a bunch of magnets in various orientations so the magnetic field almost entirely goes in one direction, and there's almost no magnetic field on the other side. So if you direct this on the inside facing into the direction of any incoming cosmic rays, the weaker cosmic rays, which are the vast majority of cosmic rays, anything, this yellow zone is all the solar flares. The next are the more common intergalactic cosmic rays, and then there's the extremely strong ones. But notice the worst of them are only 1 per kilometer per year. They're extremely rare, but these are, this is 1 per meter per second. So any little thing you do in terms of the thickness of the shield goes a long way towards cutting the radiation dose. And these lower energy ones are much more susceptible to being deflected by the magnetic ray. So if you deflect the rays in the ice or the regolith, the lower energy the thing, the longer the path it's taking, because the magnet has a stronger effect. So we can expand this into a centrifuge to augment the surface gravity. And this goes back to that starport thing that would be a ring in orbit. This is the idea of a star car. The idea here is basically you take the engine block out of the back of the Starship and you replace it with a bulkhead. And then you have bulkheads that are pre-built between each tank section. And then so you have a dock in the front and a dock in the back, and this is basically like a rail car on a passenger train where you're able to go from one car to the other through a vestibule. So if you arrange 7 of these in a hexagonal track on the same planform as the surface base, this is basically the surface base turned 90 degrees, then you could have this thing, and you could actually get 1,200 people in a ring like this. This is getting a little bit into details. You've got this 2-meter high passageway through here and so on. So it's rather interesting arrangement with all that. I did redesign this a little bit from last year, and I did change the dimensions very slightly, but so we can still get up to 1,205 people. These are all the specifics of how many cars and so forth. We would have a half car length system up here, so basically without the fuel tanks in one block on these top and bottom rings to get that half length arrangement. And then if we do a centrifuge on the moon, we can boost the gravity up to almost a little over 3/4 Earth gravity. On Mars, we can go all the way to one Earth gravity around the same speed. The bank angles are slightly different. The RPM is almost identical, and we're basing that on this center line here. So what we end up with, if we have one of these in low Earth orbit, we can do complete shielding from debris because, like I said, this is like 4 feet of concrete. So any space junk or whatever that hits the arrangement would not do that much damage. And since it's going to be made of water ice, it would be readily repaired. You can store up to 48 starships in here, refuel them, send them to a much larger base of these things stacked at L2. So it's completely away from the radiation and debris. Away from the debris. And then you're in deep space, and you can acclimate to the idea of being in deep space before committing to 3 years on the way to Mars. And then we have the lunar outpost here. We have a similar outpost on Mars, and this is our logistics system. Since you're talking about launching 1,000 starships or 500 starships to Mars in every 26 months, this gives you the ability to have them all fueled, stored in high orbit, and ready to go at once, rather than trying to get them all going in sequence at the last minute. So in conclusion, we have a system that can handle up anything from 10 people to 10,000 people within any of these environments. We make very minimal changes to Starship. We take advantage of local materials, and we provide a bridge between surface exploration and building full ports and cities on the surfaces of the moon and Mars, and also in deep space in the vision of the L5 Society and so forth. And we start breaking the problem of being able to grow food and so forth in space. So that's all we got. Any questions? Ken, you're still on mute. Hi, do we have any questions? We got 65 participants. Let's see what I got here. Okay.
Are you suggesting that we connect 8 starships together?
You're talking about on the surface? Yes, it would basically be, you'd basically have airlocks between the units to go from one to another. And if you take the same arrangement and you turn it into a ring, like these are chambers within a ring. If you look at last year's presentation on YouTube, you got more details on that sort of thing. But basically the idea here is that you stack them like that, and then you have bridges between them, sort of like skywalks between buildings in major cities. The question was, how do you land 7 starships in such proximity? You don't. You move them once they're on the surface. Same way you do at Boca Chica, frankly. Ken, are you going to read the questions, or should I
if you want me to. Did you study Project Orion, if I may ask?
Yes, I have. I actually I've read the book cover to cover, and I've also met Dr. Dyson at one point at one of these conferences. But yes, I deeply like that that project.
Okay.
Whichever one you're talking about.
And Bill asks, the star car travels on the surface, not traveling between the starport and the orbital station? Question.
Yeah, it's basically, the idea is basically if you make a ring of train cars, picture a train with no engine. And by train, I mean like a passenger train, like a metro rail, where you can walk from car to car, and that's your gravity assisted habitat. That's assuming you need one. You may be just fine on the surface. This is an augmented reality, or I'm sorry, an augmented gravity situation. So if we need to reacclimate to going back to Earth, or if there's any biological processes that really require somebody to be at one Earth gravity, then you have that option in the space. And
Okay.
it may make things easier for some industrial processes too.
And then Jonathan asked, what challenges does the in situ restructuring of these ships present? How can those challenges be overcome?
Well, as mentioned, they're basically, in the case of the lunar version, those bricks are going to be relatively permanent because we center them in place. For the Mars version, at least with the water bags, you can always remelt the water and take a bag out, put a new bag in, or rearrange them like Legos. So this was originally a Mars design that allowed you to just basically, I call it Legos inside Tinker Toys. You could rearrange anything in any way you saw fit if it became obsolete. The Moon version, it's a little more strict because you are stuck with high temperature materials, so they're more permanent if you dovetail them. Now, if you take those, let's see, if you are dovetailing them with, go back here for a second, there are two ways to interlock them. So if you dovetail them like this, then you're stuck. If you dovetail them with these, and these are like have an inflatable core, then you could drain them out and then reallocate them, even on the Moon.
Okay. Question, how would you create your magnetic field?
Just electromagnets. They could be done passively, but the advantage of an electromagnet is that if there actually is a major storm coming in, you could then amplify it. And the other thing is that you may have, like, when you're putting that many magnets and bolting them to something, there's going to be field interactions that may affect the structural integrity of the thing because you're augmenting the structure itself. So you'd want to be clever about how you arranged it so that if you have any kind of, like, that there's going to be some major event outside, like a meteor hitting or something, you could actually reinforce the structure by adjusting the magnetic field.
Okay, and closely related, are you thinking of making use of water for radiation shielding?
In the case of the Mars one and the low Earth orbit one, yes. On the Moon, the problem is that if you put water and it gets near boiling point during the daytime, that's not going to work so well. You might be able to do it at a polar base or in a lava tube, but out on the surface, you can't really just use water like that. You have to use regolith.
Okay, and then Eric sort of gave you a triad of questions. I think it's pick which one you want to answer. What are some of the weaknesses of this design, or what was a somewhat painful trade-off, and what are you still thinking about?
That's a good question. The only thing I haven't really touched on in a long time are spacesuits. And I'm not really that deep into the whole thing of setting up the aquaponics and so forth. I wish I had a good architect to work with to do the interior shots because I have ideas of what I want the interiors to look like, but I'm just not artist enough to make that happen. I don't like the fact that the corridor down the middle is only 2 meters. It would be nice if you could not have to duck your way out. I mean, that's 6.6 feet, but it's still kind of tight going from one chamber to another if it's in a centrifuge. The docking collars between tracks are relatively large, so you have to be kind of clever about how you arrange those so that they can lock together or unlock as needed. But in the end, there's a lot of little trade-offs like that, but they're mostly aesthetic rather than showstoppers.
Okay, I have a question of my own that what you said partly leads into, because at the beginning you said something about, going to Mars and living there would be something like living in a 100-year-old house, and I assumed you meant that's because something is always going to be breaking. I happen to live in a 100-year-old house, and something is always breaking, and the hardest part about fixing anything is getting to it. And in an environment where there's essentially vacuum outside, have you thought about that?
That's part of the beauty of putting those vehicles immediately inside a structure that can be pressurized, and having basically a big dumb shell on the outside that's practically like a cave wall. So anything you would keep all your guts on the inside for the most part, or on the outside where it can be serviced by robots, but you don't bury things in the walls like you do on a house typically. Ironically, I'm on Sunday I will be repairing a toilet in Beloit from like 50 years ago. And this is my second attempt because it has parts in it that are just not serviceable. So it's been fun, believe me.
Been there, done that.
Mm-hmm.
Got a new one.
Mm-hmm.
Okay, was one more. What are the advantages of low enriched uranium that make it a better choice over a molten salt thorium reactor for this application?
Lack of moving parts is one issue. Thorium is great, but you have to get it kick-started. So you actually, I believe you need a real uranium reactor to essentially get the thorium up to speed, for lack of a better word. So it's thorium is great if you have 10 years to play with and a relatively large facility. The idea here is to go straight from landing on, so it's something that you want something that can fit in a container and just run like a battery. The advantage of low enriched uranium is that part of the nuclear reaction of uranium fission is that it releases a helium atom, and this causes swelling in highly enriched uranium so that they actually break out of their little shells, and you have to engineer everything around the idea that the rod's going to get bigger as you burn it. Low enriched uranium, it runs so slowly that you don't have that swelling as nearly as badly. So the speaker yesterday was a real expert on that, and I really love his work. So that's what a lot of this is based on. I've been following him for several years now.
Okay, question from Adil Khan. How far can this invention go in simulations?
I'm not quite sure what that means. Like, could you build an MDRS on this platform? Theoretically, yeah, it just cost an insane amount of money to put it together. But there is a lot in this structure that could be just made on Earth with no problem. You're basically just building towers. I mean, it's really just a building with heavy bricks. The heaviness of the bricks is not so much of an issue on the Moon and Mars because they'll reduce gravity. But you also don't have to make things, 4 meters thick either. So that's the other beauty of this, is we don't know exactly how thick we have to make the walls, but in this design you can make them as thick or as thin as needed.
Okay, that seems to be all the questions, and we're down to our last few minutes here.
Mm-hmm.
Anyway,
yeah, I'm actually the next speaker in this next track, so I have to jump.
Right, and we still have to jump to the other next Zoom meeting. So,
okay, well, thanks everyone. I appreciate your attention.